Okay, we'll start now. Solutions to some numerical problems in quantum mechanics. This is our first numerical, that is to calculate the energies for the ground state and the first two excited states of the electron confined to a potential well of infinite height of width 1 angstrom. So, what is the expression for to find the these energies? En is equal to n square h square by 8m L square, where n stands the state. Here in our case it is asked to calculate the ground state and the two excited states energy values. So that is E1. The next excited state is the E2 and E3. E1 is a ground state, E2 and E3 are the excited states. H is Planck's constant, m you know the mass of the electron, and the length of the y, L is equal to the, that is width of the potential well. So it is 1 angstroms. So if you use this, here we are calculating the energies in electron volt, EV. Therefore, in the denominator I have divided it by 1 EV, that is 1.6 into e to the power of minus 19. So if for n equal to 1, it is approximately 38 electron volts. Similarly, you calculate for E2, you know that for E2 is equal to 4 times of E1. So you can straight away you can multiply 4 times of the first the energy of the ground state. So E1 for E2 is equal to 4 times E1. E1 is 38 EV. If you do that, it is approximately 1.5, that is 152 EV. And similarly, E3 is 9 times E1. So 9 into approximately 38 EV. So it will become 342 EV. So E2 is 4 times of 38, it's 152, and E3 is 9 times of E1. So it is 342. See that here the electron is sitting in the lowermost state, E1, that is n equal to 1. The electron sitting in the lowermost state has some positive value, that is around 38 EV. But if you look at the that is classical concepts, you may have as the zero also. Quantum mechanically, there is some positive value for the energy. Okay. Now we'll move on to the next. An electron confined to move in a potential well of infinite height, having a width 20 angstroms. Find the de Broglie wavelength associated in its ground state. Ground state means n equal to 1. Assuming the potential energy is 0. So you need to assume the potential energy 0. It means certainly you are measuring the kinetic energy, that is E equal to h square by 8ml square. We have seen that we have made an assumption in getting this expression also. We have made the potential energy to be minimum value. So the minimum value is taken to be 0. Therefore, it is represents the kinetic energy. En is equal to n square h square by 8ml square represents the kinetic energy. So if you calculate the electron in the first state, that is a ground state, so it is h square by 8ml square, and here I did not divided it by 1 electron volt, because I'll tell you why I did not divide it by 1 electron volt. I'll keep in joules only. If you want, you can express in electron volt, but here in the present case I require it should be in joules. I'll tell you why it is. So what is that? What is that is asked? It is asked to calculate the de Broglie wavelength, lambda equal to h by p. Here lambda equal to h by p. You know, h is a Planck's constant. It is in the joule second, because it is p is equal to root of 2me. You know that kinetic energy once again is equal to p square by 2m. From that you can get the momentum expression, p is equal to root of 2me. This momentum within the roots 2, that is mass of the electron, into root of e. What you got, the e is in joules. So now the momentum is this, the wavelength happens to be 4 nano. So the next numerical is the ground state of an electron in a potential well of infinite height is 5.6 milli electron volt. That is a width. L is equal to 5.6 milli electron volt. If the width of the potential well is doubled, that is the width what is doubled from A to that is L to 2L, if it is doubled to L to 2L, then what is its ground state energy? So you need to calculate the new energy of if it is doubled, the width of the potential is doubled. So you know it is ground state, therefore n is equal to 1. So the formula is simply h square by 8m L square, because n is 1, the n square is 1, therefore h square by 8m L square or A. So now this goes to double now, so L going to 2L, so h square by 8m 2L square, so it becomes 4L square. So L going to 2L and multiplied by outside 8, 0.25 E1. So that is 1/4 of E1. It is 1/4 of E1. Therefore, the new value is 1/4 of E1. You substitute for E1. That is very simple. H square by 8ml square. So 0.25 multiplied by H square by 8ml square. Or it is simply 0.25 multiplied by E1. It is already given E1 value, no? Since they have given already the E1, 5.6 milli electron volt, you can straight away calculate 0.56 milli, you substitute for EV, that is 1.6 into 10 to the power minus 19. If you want to express in EV, again divide by 1.6 10 to the minus 19, therefore it will be 1.4 MeV. So 1.4 milli electron volt, the new ground state energy of an electron, if it is doubled from 5.6 to, then it becomes 1.4 milli electron volt. A particle is moving in one-dimensional potential well of infinite height, has a width of 25. So imagine the width is 25 angstroms. Assume that the particle is in its least energy state, that is n equal to 1. Assuming the particle in its least energy state, therefore n equal to 1. Calculate the probability of finding the particle at an interval of 5 angstrom at distances a by 2, a by 3 and a. Here a is the width of the potential well. So width of the potential is 25. It is asked to calculate the probability of the particle at the a by 2. If the width of the potential well is 25, what is a by 2? It is half of that, it is 12.5. And they have given the limits in an interval of 5 angstroms. So it is in an interval of 5 angstroms. At the center it is 12.5. So what are its the extremities of the interval? So it is 10 and 15, isn't it? So the extremities of this interval is 10 and 15. At the center is 12.5. So 12.5 is at the center. So it's in an interval of 5 angstroms. Therefore, I just subtract 2.5 with 12.5. So you are 10 there, and add 2.5 to the other side. So it becomes 15. So x1 and x2, x1 is 10, x2 is 15. A by 2 is 12.5. So you are asked to calculate here the probability density. Probability density at a by 2. So you know that to get the probability density, it is a modulus of psi square d tau or dx is equal to 1. If it is one dimension, we calculate probability p equal to modulus of psi square dx. Okay. So now the interval, I have given the interval that is between an interval of 5 degree and 5 angstroms. So the limits are x1 is 10 and x2 is 15. So it's an integration from x1 to x2. So you need to calculate the probability between the interval x1 that is equal to 10, x2 is equal to 15. So modulus psi square into dx. So you know that psi n and into psi n star is the modulus of psi square. Psi n and its conjugate sin star is, their product is modulus of psi square. You look at there the psi n and psi n star. So if you take the product, this I into minus I becomes plus 1, and product of root 2 by a, it becomes 2 by a. Okay, and it is sin square x. So look at there integration. So P is equal to x1 to x2 modulus psi square dx, that's equal to x1 to x2, and root of I go become it will become plus, therefore root of 2 by a, that is square of that sin pi x by a. So altogether it's taken in the square bracket square. If you square that, it is x1 to x2 2 by a sin square pi x by a into dx. I'm not taking here n, already consider n equal to 1. Otherwise I would have been there n pi something like that. So it is, since it is a least general state, n is already substituted, it is 1. So you know from mathematics how to integrate sin square theta. You use 1 minus cos 2 theta, isn't it? Half into integral of sin square theta is equal to half of 1 minus cos 2 theta. So that is used here. So you x2, that therefore probability P is equal to 2 by a integral x1 to x2 half into, that is a bracket, square bracket, 1 minus cos of 2 theta. So if you do that simplification, you can try. If you do that simplification, we will find that the P is equal to x2 minus x1 by a minus 1 by 2 pi, that is within the brackets, flower bracket, sin of 2 pi by a into 2 and minus sin of 2 pi by a into x1. So here it is not 2, that is x2. Within the small brackets 2 pi by a, that is not multiplied by 2, it is x2 minus sin of small brackets 2 pi by a x1. Probability P is equal to x2 minus x1 by a minus 1 by 2 pi within the flower bracket sin of 2 pi by a x2 minus sin of 2 pi by a x1. So now it is asked to calculate the probability at a by 2. The probability is at a by 2. Therefore, what is x1? x1 is 10, x2 is 15. Since a is 25, and we have already seen that a by 2 is 12.5. Therefore, x1 is 10, x2 is 15. So it is 15 minus 10 by 25 minus 1 by 2 pi sin of 2 pi by a. How to get this 2 pi by a? It is 360 degrees, pi is 180 degree. So 180 into 2 is 360 divided by 25. Okay, 360 divided by 25, it becomes 14.4 degrees. Okay, so then you substitute this 14.4, that is with this power bracket, sin of 14.4 x2 minus sin of 14.4 into x1. So you got P is equal to 0.2, that is 15 minus 10 by 25 is 0.2 minus 1 by 2 pi, power bracket, sin of 14.4. Now what is x2? x2 is 15, then sin of 14.4 multiplied by 10. Okay, you substitute this, you will get the answer as 0.387. The probability at the center of this box having a width of 25 angstrams within the limit of 1 and x2, where x1 is 10 and x2 is 15. The probability will be 0.387. It means it is 30 or around 40% or 38.7% of find the probability for the particle at the center of the box. Now if you try later on, I think it is a homework, you calculate the probability at a by 3. A spectral line of wavelength 0.461 angstrom has a width of 10 to the minus 4 angstrom. Calculate the minimum time spent by the electrons in the upper energy state. So the formula here with respect to isolation principle for energy and time, that is delta E is equal to delta E delta T greater than or equal to h4 pi. Delta E delta T greater than or equal to h4 pi. So you need to calculate delta T, minimum time spent. Therefore delta T is greater than or equal to h by 4 pi delta E. Now what is delta E? Because here they have given the wavelength, that is the spectral line of wavelength has been emitted, isn't it? Therefore, the wavelength is 5461. It is a photon. So it is around a point 7 point something. You will get it on point 0.7 or something now. So it is, I mean, 7 point something seconds you may get in 10 to the minus 9. So I approximated it to 8 nanoseconds. This is another examination problem. The position and momentum of 1 keV electrons are simultaneously determined, and if its position is located within 1 angstrom, what is the percentage of uncertainty in its momentum? The position and momentum of 1 keV electrons, 1 kilo electron volt electrons are simultaneously determined. Here both on position, they are simultaneously determined. And if the position is located within 1 angstrom, what will be the percentage of uncertainty? It is not the it's uncertainty, it is the percentage of uncertainty in its momentum. So what that is, delta p by d should be calculated. The meaning of percentage of uncertainty momentum is delta p by p into 100. Okay, you know that. See, suppose if I ask to calculate your percentage of attendance, how do you do that? So number of classes present to the number of classes taken, isn't it? That's how we'll calculate the percentage of attendance. So it is a percentage of momentum is delta p by p multiplied by 100. So now it is asked to calculate this ratio delta p by p. So you want delta p and p. Electrons are simultaneously measured. If the position is located within 1 angstrom, that is delta is 1 angstrom. So formula is delta x delta p greater than h by 4 pi. Therefore, delta p is greater than equal to h by 4 pi into delta x. Substitute delta x here, this 1 angstrom. So what you get, it is delta p. Got it?